This is the second lesson on financial applications. Last lesson we looked at simple interest and compound interest. Today's lesson is something called present value, which is just really a rearrangement of the compound interest formula. So you may remember, hopefully, that the compound interest formula is A, final amount, is equal to the principal, P, times 1 plus I, the interest rate per compounding period, to the exponent n, which is the number of compounding periods. Sometimes we call that formula future value because it calculates how much money you will have at a later date. So P is, you can think of P as the amount of money that you invest now, then A would be what you have later, right? After you've earned some interest, then A is the amount that you have at that point. So it doesn't matter when the time is, as long as you understand that P is a time period that comes before A. So they could both have happened in the past, they could both have happened in the future. So we don't get hung up on the fact that it says future. It doesn't have to actually be in the future, but what does matter is that the time, the amount of money at time, the amount of money P occurs at time before A. So present value is just working backwards. We know how much money we want to have in the future, which would be A, and we have to calculate how much money we need to invest now in the present to reach that goal. So we can rearrange this formula A equals P times 1 plus I to the n, because we know A, that's what, that's what we want to have, and we know how much that is, and we want to solve it for P. So rearranging the formula, we're going to get the following. Here's the steps. If I start with just writing down the formula, 1 plus I to the n, and I want to isolate P. So obviously I'm going to divide both sides by 1 plus I. So I'd have A over 1 plus I, and I need to keep them in brackets still, that 1 plus I, to make sure that I add them together before I do the division. And instead of writing it as A over 1 plus I to the n, I could write it as A times 1 over 1 plus I to the exponent n. So just sort of breaking it into a fraction times that letter A. And then if we do that, remember what we know about exponents. If we had something like, say, 2 to the negative 1, that's the same as 1 over 2 to the positive 1. Or if I had 2 to the negative 2, that's the same as 1 over 2 to the positive 2. So I could work backwards. I could start with something like 1/2 and write it as 2 to the negative 1. Or I could start with 1/4 and write it as 2 to the negative 2. Well, likewise, I can start with 1 over 1 plus I to the n and write it as, wait for it, 1 plus I to the negative n. So that's where the formula comes from. This is the formula we're going to use today. So just, in the end, all you really need to know is that P and A have switched places, and there's now a negative exponent in front of n, or negative sign in front of n, which is the exponent. That negative exponent is what's going to let us work backwards to get a smaller amount of money. Obviously, compound interest causes money to grow. So if I have, so that's just for argument's sake, say I want 5 years from now, I want to have $100,000. I'm going to have to invest some money now so that it grows to $100,000 in 5 years. How much is it? I don't know. It depends on the interest rate and the time, the 5 years. What I know for sure, though, is it's going to be less than $100,000. I'll put in, maybe it's $80,000 or 85 or 70. Again, it depends on the interest rate. But it's going to be some amount less than $100,000. Then when interest and time work on it, it's going to grow to $100,000. Well, this formula works backwards. I put the $100,000 in for A, along with the interest rate and the time, and with that negative exponent there, it's going to cause me to have a smaller amount. It's going to tell me what that smaller amount is that I need to invest. So Otherwise, other than this different formula with that negative exponent and those couple variables swapped, everything works the same. I still need to know I still need to know n. So I'll do it just like in the last lesson. So here's a couple of examples. So for A part, there's two examples here, A and B. They're just set up as a table. So for A part, my interest rate is 6.4% per year. Compounded quarterly, which is 4 times a year, 6 years. I want to have $30,000 at the end of this. So the interest rate per compounding period is 0.064. We change it to a decimal. Divide it by 4 because of the quarterly. And 0.064 divided by 4 is 0.016. N is going to be the 6 years times 4 times a year, which is 24. And again, then we just put it into our formula. But the new formula is P equals 30,000. That's the amount I want to have at the end of 6 years. Times 1.016. I added 1 to I to the negative 24. When I type that in, what I'm going to get is an amount less than $30,000. $20,496.15. So again, what that's telling me is that if I invest $20,496.15 today, and I am able to get 6.4% interest, and I let it sit for 6 years, at that time, after 6 years have gone by, it'll be worth $30,000. B part, just the same idea, different numbers. So I is going to be 0.021 divided by what? Well, divided by 12 because it's monthly. Now that's one that I'm going to need my calculator to help me figure out. Don't have that at my fingertips. 0.021 divided by 12, 0.00175. And N is going to equal 9.5, 9.5 years times 12. That should be 114. Since 10 times 12 is 120, I'll take away 6. I get 114. P is going to equal $25,000 times 1.021 to the exponent negative 114. And again, it's just a matter of typing everything into the calculator. Let's see. Forgot all the values already. 25,000 times 1.00. It's not 21 though. I realize I wrote something wrong here. This number is not my I value. My I value was 0.00175. So 00175. 175 to the exponent negative 114. $20,482. I'll come back for the rest. And 8 cents. Similar amounts, but they grow to different values because of different interest rates and different times that they're invested. Actually, the one that is invested a shorter time, 6 years, grew to a larger amount, 30,000, but the difference was in the interest rate. Very hard to get a 6.4% interest rate in today's financial markets. The present value formula is also used to calculate amounts borrowed on loans from banks, credit cards, etc. Remember, for present value, we always work backwards in terms of time. So in other words, if there's multiple steps, we start at the end and we work backwards towards the first one. Paul saved $500 to buy type O or misspelling mistake anyway. To buy, nope, a gaming computer. He borrowed the rest at 19.9% per annum, per year, compounded monthly, 12 times a year. 3 years later, I don't think we want the word one there. 3 years later, he paid $1,798.75 for the principal and interest. How much did the original computer cost? So, to work backwards, basically, the $500 is something. Imagine you go to a computer store, you give them $500 as a down payment, then you're going to pay the rest off monthly. So if I'm working backwards, the last thing I'm going to do is I'm going to add $500 to find the original cost. So I can ignore the $500 for now, and I can calculate I and N and use the $1,798 as my principal. So N, well, since I wrote that down, it's going to be 3 times 12 because it's monthly, so 36. I is going to be a big decimal because it's going to be 0.199. Very high interest rate, but when you're borrowing from a business, often they do charge high amounts from a retailer. So 0.199 divided by 12, 0.016583 repeating. 0.016583. All right, so P equals 1798.75 times 1.016583 repeating to the negative 36. Not sure if I got those numbers right. 6583 repeating. Now, repeating means obviously it goes on forever. I don't need to add this many decimals, but it's easy, so let's add a whole bunch. Negative, and I forgot the number of years, 36. 36 months, 3 years. 995, okay. So the present value is $995. And then, so that's how much he had to pay off on the loan, which means that he walked into a store, paid $500, and then he had to finance the $995 that was left. So the original cost must be the $995 plus that $500. So $1,495. Isabel is investing $800 that she would like to grow to $1,500 in 3 years. At what annual rate, compounded monthly, must Isabel invest her money? So for this one, we're being asked to calculate the interest, right? So we don't know what I is. We do know, if it's compounded monthly, that it's going to be whatever the annual rate is. I'm going to call that R for annual rate. I is going to be R divided by 12. That's just something to maybe keep in the back of our minds for now. N is going to be 3 years times 12. So 36. And she wants to invest $800. That would be P, that's the initial amount. A, the final amount, is $1,500. I can use either formula for this. I could use A equals P times 1 plus I to the N, or I could use P equals A times 1 plus I to the negative N, because in both cases, I know A and P and N, they're really the same formula rearranged, so it doesn't matter. Maybe I'll just use the straightforward compound interest one we learned last class because Why not? Why make things more complicated with a negative exponent? So I will put 1,500 in for A. I will put 800 in for P. I've got 1 plus I, and I've got 36. I need to solve for I now. So I just isolate I by working backwards, doing opposite operations in the opposite order. So I'll have 1,500. I'll divide both sides by 800. And then I will end up taking the 36th root of each side. So 1,500, I know I could work that out, but I'm just going to write it like this for now. Figure out what that is, then take the 36th root. That's going to leave me with 1 plus I. And then the last thing I would do is I would end up subtracting 1 from each side so that I've got I by itself. So let's do all that at once. 36th root of 1,500 divided by 800 minus 1. And that minus 1 has to come outside the root sign. So I've got this big long decimal, 0.17614. And there's more. I'm going to write them all down. 69226. And the reason for that is because I want to wait till the end till I round so I don't introduce rounding error. Because remember this part back here, I'm not quite done. What I calculate is I, the interest rate per compounding period. So about 1.7%. But the annual interest rate would have to be 12 times that. Because that's what banks generally give their money, give their rates as annual rates. So we need to be able to work backwards to get that. So R is going to end up equaling, as we can tell from, again, this formula here, R is going to equal 12 times I if I rearrange that. So I times 12, I don't want to write all those digits down again, but all those digits on the line above, I've still got them in the calculator. I can just say answer times 12, and I get 0.2 or 0.2114. 0.2114, which is the same as 21.14%. So, in other words, it would take a very high interest rate, 21.14%, to grow something from $800 to $1,500 in 3 years. It doesn't matter what the amounts are, but if we look at P compared to A is almost double. She's hoping to double her money in a fairly short period of time, 3 years. So it makes sense that the interest rate would need to be quite high.